Number 8. It takes this much energy in joules to remove one electron from a metal surface. What's the wavelength of light capable of causing this effect? So it takes this much energy to get the job done. Therefore, the energy must be supplied by something. It's going to be supplied by the light. And if the light has that much energy, then what's its wavelength? Now, this one gets a little bit more complicated, so brains turned on. I know the energy, which is in this equation, right? But there's no wavelength in this equation. Wavelength is in this equation. But notice that frequency is in both. So if I could solve for frequency, I could put it here, and then I could solve for wavelength. So I'm going to put my energy, Planck's constant, which I know from the front of the other side, the top of the other side, and this number divided by that number. The joules cancel out. It gives me per seconds as the unit, and I get my frequency number. I can put that here. Speed of light is always the value from the top of the other side. Wavelength is the unknown. This divided by that gives me the value for lambda, wavelength. The per second part cancels out, gives me meters. Now, here's the thing to watch for. When you get E negative 7 times 10 to the negative 7 meters, there's a chance it might be visible. Go and convert it to nanometers times 10 to the negative 9 meters to see if it's visible. I got to get the exponent on 10 from negative 7 to negative 9. Going from here to there is getting smaller. More negative is smaller. This number got smaller by 2 decimal points. This number must get bigger by 2 decimal points. Now I have 247 nanometers, and if you look at the colored part of your electromagnetic spectrum paper that I posted, you'll find that that doesn't reach the visible spectrum. It's too small. It's off to the left. That's still in the ultraviolet range. It's not visible. Also, I had to change this number to make a better illustration of my point. So this much energy in joules, same idea. What's the wavelength? It's really the same kind of problem, but we're going to get a different sort of answer in a way. We're going to take our energy, Planck's constant. I'm going to find the frequency so that I can put that value over here. This divided by that gives me frequency. Take that value, put it over here. Speed of light I always know. This divided by that will give me wavelength in meters. But when you're dealing with 10 to the minus 7 meters, there's a chance it might be visible. Change this number to negative 9. That should be a negative. This got smaller by 2 decimal points. That should get bigger by 2 decimal points. And now we have 658 nanometers, and that is what I would think we should call the orange range of visible light. So if we talk about transferring these numbers into something we can use, we need to know these things here. That's an angstrom, by the way. There was a Mr. Angstrom, and I think he was Swedish, so it has that little funny little circle up there. And it means 10 to the minus 10 meters. And nanometer literally means 1/billionth of a meter. So it is 10 to the minus 9 meters. And I don't know if you ever thought of it this way, but since we know that 100 centimeters is 1 meter, 1 centimeter is also 1 times 10 to the minus 2 meters. So let's convert 500 centimeters. Well, it's 500. What's a centimeter? A centimeter is times 10 to the minus 2 meters. So some people can just leap to the correct answer automatically in their head, but I'm going to try to explain it all the way out. 500, 10 to the minus 2 meters. But in real scientific notation, it's digit dot. The decimal goes after the first digit that's not a 0, so the decimal needs to move from being here invisibly to being there. So I'm going to move the decimal 1, 2 spots. This got smaller, So this must get bigger by 2 spots, and we get times 10 to the 0 meters. Also, this is times 10 to the 0 meters, but anything to the 0 power is 1. So it's 5 times 1, or just 5 meters. And isn't 500 centimeters 5 meters? Sure it is. How many hundred centimeters is 500? This is 5 sets of that. So it is 5 sets of meters. It is 5 meters. An angstrom is times 10 to the minus 10 meters, so that's 2,300 times 10 to the minus 10s of meters. But the decimal needs to go back to here after the first digit that is not a 0. This got smaller by 3 decimal points. This must get bigger by 3 decimal points. And bigger is less negative. 14 nanometers means 14 of 10 to the minus 9 meters is. But the decimal needs to go here. This got smaller by 1 decimal point. This needs to get bigger by 1 decimal point. This means throw on 10 to the minus 9, but the decimal belongs here. This got smaller by 2 decimal points. This must get bigger by 2 decimal points. Those are pretty much repeats. If you convert this to nanometers, you get 230 nanometers, because we got to make this be minus 9 to see if it's visible. This is going to get smaller by 2 decimal points, so that it turns into minus 9. This is going to get bigger by 2 decimal points to make up for it. Now I have 230 nanometers. But go look at the colored portion of your electromagnetic spectrum that shows us the spectrum of human visible light, and 230 nanometers is not visible by humans. It's off to the left in the ultraviolet. 14 nanometers is way off to the left in the ultraviolet. 500 centimeters is in the e to the 0 times 10 to the 0 section. That is in radio. 690 nanometers, look at the colored section, I think is red. This is way down the scale in the times 10 to the 0 spectrum in that section, and it's radio. And this is a little too big to be visible to human beings, so this is a little bit off to the right, and it is in infrared. Which wave above carries the shortest and the greatest energy? We talked about in a previous video that the faster the bounce, the more energy. That also goes with the shortest wavelength. If you need to hit pause, then do that, but go back and look at your electromagnetic spectrum page, and as the frequency gets greater in one direction, the wavelength gets smaller. And it also has an energy arrow, and as the energy gets greater, the wavelength gets smaller. So the greatest energy will have the shortest wavelength. Which one of these is shortest? That one is 10 to the minus 10. Which means I am wrong. Is used for blah 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 blah. Frequency is nu. What is the wavelength? Lambda. And color. What is the wavelength? Well, that's not all that hard to find. We're just back to our formula. that involves wavelength and frequency. They told me the frequency. I always know the speed of light. This divided by that gives me wavelength. If it's 10 to the minus 7, push it over to be 10 to the minus 9 so that it's nanometers, and you can check if it's visible. This is the scientific notation for something we call nanometers. And if you look at the colors, 652 nanometers is orange. Calculate the energy of an X-ray photon. Wavelength. I want energy. Well, I do have a formula that has energy. But it doesn't have wavelength in it, does it? So what I can do is I can take my speed of light formula. Speed of light equals wavelength times frequency. I can find frequency and put it into my energy equation. So I'm going to take speed of light divided by the wavelength they gave me, divide this under, find frequency, put it into my energy formula, and multiply it by Planck's constant, which is at the top of the other page. This seconds cancels out that per seconds and leaves me joules.